Hello and welcome to my lab on black holes. So the purpose of this lab is to calculate the mass of a black hole to determine the appropriate initial velocity of the ship in the second part of the calculations, and then to display knowledge of gravitation, Newton's laws, and other aspects of physics. So the physics we'll be using here are Newton's second law, which will be very prevalent in both, but especially part 2, where we will be looking specifically at the specific parts of forces for every object in the system and surroundings, and how all of the gravitational forces interact with each other. And we'll also be using universal gravitation to determine these gravitational forces, as the forces of gravitation are the only forces that will be present in our part 1 and part 2, as they are in isolated spaces. And we will also be using the velocity position update formulas in part 2 to determine the new velocity position of each object based on the forces acting on them. So the reason for the laws and models: first, Newton's second law is being used because it's used to determine the velocities and accelerations of all the objects, and to determine the specific parts of forces that are interacting with other objects in the system. We'll also be using curving motion and momentum, because all the objects are going to be orbiting around a black hole, and there'll also be universal gravitation being used, as the forces of gravity is the only force being used by all these objects. And then GlowScript is the computational software we're doing everything on. So, a preview of the results. First, we have the mass of the black hole, which is around 8.67 times 10 to the 23rd kilograms. We have the initial velocity of the ship, which in the x direction is around negative 12 million, and in the y direction is around 6.899 million. Yes, and so the system and initial conditions for part 1. First, the mass being found is the black hole. The mass of the star is 2.0 times 10 to the 30 kilograms. The initial time will be 0, and the change in time is 1 day, or 86,400 seconds. The gravitational constant is 6.78 times 10 to the negative 11. And then the system that we'll be looking at is the black hole, as that is the mass that's the object whose mass we're trying to find. And then the star and the space around the whole black hole are the surroundings. And here we can see the code. If you look to the right, you can see all of the parts that went into finding the specific momentums and forces that ended up being used in the bottom equation to determine the mass of the black hole. To the left, you can see the code that we use to determine the arrows as the So this simulation has been sped up to fit into the video, but that is our first part. Now, here are the initial conditions and the system for part 2. It's pretty similar, except that the mass of the star is changed, and the mass of the ship is given because the ship is added into the system. And the mass of the black hole is the same, because that's the mass that we're using for this part as well. And then the change in time is now just 1. And the system is the ship, while space black hole and star are the surroundings. And then part 2 of the programming. Here on the left, you see the mass of the black hole, and then on the right, you see all the code that went into determining the forces that were acting on all the objects in the system. And if you look back to the bottom left, you can see the velocity that we found that is able to have the ship escape the orbit. The simulation has also been sped up a little bit, but this is our second part with the ship trying to escape the black hole. So the two different parts of this project had similarities and differences. We saw that they both utilized the mass of black hole and forces in the system, requiring universal gravitation as calculations that needed to be done. We also saw that both models dealt with orbits and gravitation and Newton's second law. However, in differences, part 1 was to find the mass of a black hole, while part 2 uses this mass to find necessary initial velocities for the ship to escape orbit. And part 2 also required determining more forces between objects. So some sources of error that happened were that we saw part 1's program ran for a relatively short time period, and so the exact mass of the black hole was most likely not completely accurate. And guess and check was also used to find the initial velocity of the ship. And then, so how net force and components differ from momentum? So first, we see that net force is equal to the change in momentum over change in time. So the net force is the actual change in the momentum based on a change in time. The net force is what actually causes this whole change in momentum. And also we see that the different parts of each net force can change the momentum, as they can affect the way that the object motion will be after the force has been exerted. And we also see that net force is based more on acceleration, while momentum is based on velocity. So the force is what actually accelerates an object to have a change in momentum. It's also much more difficult to determine the magnitude of force than it is to find the change of momentum, which is why finding the change of momentum can help get the magnitude of force. So what if we enter orbit? Well, to bring the ship into orbit, velocity had to be decreased, and the y speed was increased, while the x speed was decreased much more as a result. The x speed also had to stay negative, so that the object went into the gravity of the black hole rather than out of the gravitational field. And here we have the velocity that we got to put the ship into orbit. And to the right, you can see the orbit. So some conclusions we found were that using Newton's second law of universal gravitation helped us calculate the mass of the black hole, the initial velocity of the ship, and the initial velocity for the what-if orbit. And through all of this, we observed ways, forces, and momentum differ. Thank you for watching.